Hi friends, the next issue to discuss in the scheduling algorithms is the round robin scheduling. This is designed especially for time sharing systems where multiple processes want to use uh, available limited resources on time sharing basis. Usually it is similar to first come first serve scheduling, but under preemption it works. So in this preemption is added to enable the system to switch between the processes. In the original first come first serve basis type of scheduling, the process that has come first is allotted the CPU to run, and that process will leave the CPU only when its work is done. Till then it will not allow CPU to work for any other process because it was non-preemptive type of scheduling. But round robin works almost like a first come first serve scheduling, but preemption is there so that while one process is running we can stop it and make other process to run on a round robin basis. In this small unit of time called a time quantum is defined, and after every time quantum the process changes its place. So the process which is running will stop running and gets into the ready queue, and the next process in the ready queue comes back to running state, and after every time quantum this cycle repeats. So let's take an example. Only with example we can understand any concept. So let's take an example which has got three processes P1, P2, P3, and let us simplify the problem saying that there is no arrival time. In this case everything has come almost on the same time, and P1 has a burst time of 24, P2 has a burst time of 3, and P3 has a burst time of 3. Now if it was a simple first come first serve, then P1 will be executed, so it takes 24 units of time, then P2 takes 3, then P3 takes 3. So in all, in 30 units of time all the three processes complete their job. But looking at the waiting time, P1 has no waiting time, P2 has to wait for 24 units of time till P1 is completed, and whereas P3 has to wait for 27 units of time till P1, P2 both are completed. So average waiting time was quite high. Now if we change this and make this whole thing as a preemptive type of thing, that means each process gets its own turn on a cyclic basis for a period of time quantum, and the advantage of this is if three processes are running in this time sharing manner, round robin scheduling manner, then after some number of quantum slices, time slices, each will get its turn, and if these processes are under the human observation, then for a small time it may not be active, but now and then it becomes active. So round the clock it becomes active now and then, but for the human, because of slow response of the human looks at the screen, understands it, and all that takes some milliseconds, but the processor is working in nanosecond. So the whole switching is done in nanosecond speed, then definitely human will not be able to understand that something went on off and all that. So human feels that all three are running simultaneously, all three are on all the time. So that's the advantage of working with round robin scheduling. Let's look how this situation is working if we work for say time quantum of 4 units. So as usual, P1 gets its turn. After 4 units, the scheduler says P1 to stop. Other processes are there waiting, so please stop. So P1 stops, and then P2 gets its time of 4 units of time, because time quantum is 4. So for 4 units of time, P2 gets the chance, but P2 needs only 3 units of time. So after 3 units, P2 is done, and now P3 gets its chance for 4 more units of time, 1 quantum, but P3 also needs only 3 units of time. Therefore, after 3 units of time, P3 also completed. Now we are left with only P1, so we keep on giving the 1 quantum to P1, and then look, anybody else is waiting? No. Then again P1. Anybody else waiting? No. Again P1. Anybody else waiting? No. Again P1. So that way, first we start with P1, then P2, then P3, then again 5 slices of P1 will continue, because in all, with one time slice having 4 burst time, then 24 burst time needs 6 slices. So P1 we can count that there are 6 P1s, 1, 2, 3, 4, 5 and 6. So 6 quantum. Now what is happening, if you just look it carefully, so at the user's point of view, if user is working for P1, then the moment the system starts, P1 comes into life. And before a human could understand that P1 stopped, P2 starts. So the one who is interested in P2 sees that within 4 time slots P2 started, but these 4 time slots are so small that infinitesimally small that human cannot understand that P2 started after 4 time slices or time slots. Therefore, the human thinks that P2 also started in the same instant. Same way P3. Then, as long as P1 is concerned, P1 gets a response in the first slot itself. Then for 2 slots P1 is not working, but these 2 slots are so small for the human to notice that by the time human is able to notice, again P1 started executing. Therefore, for the one who is interested in P1 doesn't notice the gap where P2, P3 occupied. For person with P2, this small gap, a delay of starting execution, that is the response time P2, 4 units of time, is almost negligible for the human. Same way for P3, the response time is 7, so that also looks almost negligible. So all the 3 processes appear as if they are running together in parallel, as if each one has their own processor, their own CPU, but in reality there was only one CPU and they are running one after other in a loop, and these gaps are so small that we will not be able to notice it. So round robin scheduling is a preemptive CPU scheduling algorithm where each process gets a fixed time slice or quantum to run. It works like a rotating turn based system and very fair and predictable. So we know that first if P1 comes, then P2 comes, then P3 comes, then P1 comes, then P2 comes, then P3 comes, and so on. If each one P1, P2, P3 are having the burst time very much greater than the time slice or time quantum, then these get repeated P1, P2, P3, P1, P2, P3, P1, P2, P3. So we know that in what order they are repeating, and each one definitely comes after 3 rounds. P1 comes after 2 more gaps, then P2 comes after 2 gaps, P3 comes after 2 gaps. So it is very fair and definitely predictable that if P1 has come now, and if there are 3 processes running in the ready queue, then the P1 will repeat after every third time slice. So the type is preemptive. Decision is based on the time quantum, not on the size of the process burst time and all that. Doesn't make any sense with respect to burst time, like it was done in shortest job or shortest uh, remaining time algorithms. Here it only depends on the time quantum, and usually done with first come first serve logic with preemption and very high fairness, because every process gets a turn in every cycle, and definitely no chance of starvation, because if there are n cycles, then in first n time slots everyone gets one chance. So in every nth turn each one will get a chance. Therefore there is no question of any process being starved. So looking at the advantages, it is very fair and simple to implement, excellent for time sharing systems, and it prevents definitely starvation, and good response time for interactive tasks, because it's everyone is getting a share in the round cyclic way. So the interactive, when you say that human is working with that, like pressing a mouse button or typing something on the keyboard, and the speed with which human is working and the speed with which the process is working is almost quite different. Therefore the speed with which human is interacting, in that many time quantums can be used for some other processes without the user noticing that the system was not available to the user for some time. Coming on the disadvantages side, the performance heavily depends on the time quantum. What is the time quantum? How much it is? So if it is small, what happens? If it is large, what happens? That's what the problem with. Let's see what it means very soon. So too many quantum switches if the time quantum is too small, and definitely not optimal for batch system. So if you are talking about batch processing, then this one is not optimum. So the properties, round robin performance, if you look at it, CPU utilization is moderate. That depends on the quantum. We'll shortly look how it varies. Turnaround time is moderate, waiting time is low for if short jobs are there. Response time is good because each one almost immediately responds. That means if there are n processes in the ready queue, then the response time can be maximum n minus 1 times the time quantum. That is the last in the loop. So that is n minus 1 times it may have to wait for getting its turn. So response time is very good. Definitely no question of starvation, and yes, preemption is required for that. Now the issue is effect of time quantum on our performance. If the time quantum is very small, then what happens? Every now and then the process has to change. So context switching, which means switching the CPU allotment from one process to another process. So if it is the time quantum is too small, let's say 2 milliseconds, then after every 2 milliseconds the process has to change. So what do you mean by changing the process? As we discussed in the initial period of the process management, there is a process control block, and that process control block has to be updated every time a context switches. So too many context switches, then every time a new code has to come onto the main memory. Every time it has to change the program counter, the various other register values, and all that has to be modified. So that calls for very high overhead and definitely very poor CPU performance, because most of the time it is busy in copying in the new process and copying out the old process. So getting in the new process and getting out the old process, this is a major work than actual processing. Therefore the CPU is wasting most of its time just in copying the context in and out. And definitely a fast response time, because the time slice is very small. Then if it is 2 milliseconds, then if there are n processes in the ready list, then maximum 2n milliseconds required for responding to any process. Yeah, that's the only positive part of this. If the time quantum is too small, the going to other end, other extreme, if it is too large like 500 milliseconds or so, definitely context switches size are very small, so we can say it is efficient compared to the overheads and all that. We have very few overhead, and because you are not wasting time on writing, rewriting and all that, so definitely our CPU time is being utilized for executing the actual code instead of copying in and out the context switchings and all that. So it is better if we have too large time quantum, but our problem is it just looks like simple first come first serve logic, and definitely very poor response time for short or interactive tasks. If the task is very short and if it happens to be at the end of a third or fourth or fifth position, then after 3 4 5 times 500 milliseconds only it gets chance to come up first time. Therefore very long response time is there for that, so it is very poor in terms of response time, and definitely not suitable for interactive tasks, because one task is getting 500 millisecond, then second one gets 500 millisecond, third one gets 500. Say if my changing this mouse is a tenth in that loop, then after every 10 rounds my motion or my mouse movement is observed. That means 10 rounds, that means after every 5 seconds my mouse is observed. So for 5 seconds it looks here, after 5 seconds suddenly it jumps here, then jumps here, then jumps. So it doesn't make you feel that it is moving with my hand movement, but I try to move the hand movement, but till 5 seconds it is shown here itself, but after 5 seconds suddenly it jumps here, and that makes it too irritating for the user, and definitely is not for interactive tasks. Now you can think of something in between, so which we can call optimal time quantum, maybe 10 to 100 milliseconds. So it is 10 to 100 milliseconds is not too small to have large number of context switches, therefore overhead is not very high. So there is a very good balance between CPU efficiency. So this was having a very good CPU efficiency, and this was having very poor CPU efficiency, and this was having a good CPU efficiency, this is having good response time. So it's a balance between good CPU efficiency and good response. So that's what we can think, and a smooth multitasking is possible, and very good user experience we do have, because in 10 millisecond it is changing its position, and 10 millisecond is so small that we cannot notice that for 10 millisecond our mouse pointer did not change its position. So after every 10 milliseconds or 100 milliseconds it is changing its position, then we will not be able to notice it, and that makes things smooth changing, and it will have a good user experience and all that. So that's all about the scheduling algorithm, which we call round robin scheduling algorithm. So hope you enjoyed this journey. Please do like, comment, share, and please subscribe to this channel. Thank you.